Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Bhishek Manek with us today. Hello, Bhishek.
Hi, Frank. Nice to be here. Thanks for inviting.
Oh, you're so welcome. And it is August 30th of 2024 as we record this. And Bhishek, what's your geolocation? Where are you located at?
Well, I'm based in Boulder, Colorado, among the Rockies. Yeah,
Front Range.
yeah, I'm
So
at
is
last.
is is fall starting in the Rockies? Are we still sort of in summer mode?
Still in the summer mode, but I anticipate very soon we'll start seeing the colors and everything. It's
Ooh.
starting to get a bit chiller compared to a few weeks back. So yeah.
Yeah. So I'm here in Phoenix, and we'll definitely still hit our triple digits today in the afternoon. But it is starting to cool off in the morning a little bit. Definitely about 10 degrees cooler in the mornings these days. So yeah, we're getting there.
Yeah.
You throw darts?
Yeah, I started doing it just as a fun thing to do when I
Yeah.
hang out with friends and such. But mostly whenever I'm free, I do try it out.
Very cool.
It's a fun thing to have around.
Very cool. Very cool. So you have your own custom darts that are weighted and all that kind of stuff?
Um, I'm not that particular and not that an expert on that, but I do have many darts of different kinds, so I just play around with them. Yeah.
Nice. Very nice. Very nice. And Bishek, what do you like in between darts? What do you like to do for research?
Yeah, so my research focuses on sun, in particular, things like magnetic flux emergence, solar
Cool.
interior, solar convection, and those sort of things. I've been interested in some of the observations, though I don't do them particularly on my own, but I focus on numerical simulations and theory of these sort of things.
Cool. Very nice. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. Go grab a copy. On the origin of solar hemispheric helicity rules, rise of 3D magnetic flux concentrations through a background magnetic field. And Bishek, take us away.
Yeah, thanks. Yeah, the title's a mouthful, but yeah, I'm gonna talk about this article that we recently published with Nick Brummel.
Mhm.
He was my PhD advisor at UC Santa Cruz, and this is sort of one of the works that came out of it in a series of things that we published on this subject.
Nice.
This one focuses on 3D flux concentrations rising through a background field,
Mhm.
and it delves into some of the observational implications of such simulations.
Cool.
Yeah,
Okay. Good shout out. Good shout out. Okay. Here we go. Let's roll.
yeah. So there's for this work we had two different motivations. One was
Okay.
observation based, one was theory and simulation based. Um, in observations, we know very well some of the very like well-known observations on the sun of magnetic fields, like the butterfly diagram,
Mm-hmm.
the Hale's polarity law, which says something about the leading and lagging polarities and how they switch every cycle, and how they are in the how they are different in the northern and the southern hemisphere.
Right. Yep. I'm with
Uh,
you. Mhm.
yeah, in the Joyce law. So these are the traditional magnetic field observations that we have always seen on the sun. We are focused on some recently observed new active region laws called the solar hemispheric helicity rules.
Mhm.
Um, these rules focus on helicity, as the abbreviation says. They focus on magnetic and current helicity in particular. So magnetic helicity is like A dot B, which is vector
Mhm.
potential and magnetic field,
Yep.
a volume integral.
Mhm.
The current helicity is current density dot magnetic field, a volume integral again. What
Okay.
the helicity rule tells us, like, first of all, what is helicity, right? I mean, helicity, magnetic or current helicity, it just describes the complexity of the underlying field, the magnetic field over here.
Yep.
um, so basically, like higher the magnetic helicity, higher the complexity of the magnetic structure that you're observing.
Yes. Okay.
And helicity also comes with a sign, so it's a signed quantity, so it has a handedness, positive or negative,
Yeah.
and that sort of forms the very basis of the hemispheric helicity rule that we observe. Helicity rule has some very peculiar things where it says that if you observe active regions on the northern hemisphere of the sun,
Hmm.
they tend to have negative helicity. So there's a certain sort of handedness in the active region,
Yes.
which is what predominantly is seen. So it's a weak rule. So like around 75%, 60% to 80%, depending on the period or the cycle, depending on the time period where the solar cycle is, you
Okay.
may have some variations to it. But on an average, it's about 60 to 75% of the time you see this sort of phenomena.
Okay.
And consequently, in the southern hemisphere, you have positive helicity observed in the active regions. So
Hmm.
again, very preferred handedness is observed on the solar atmosphere when we look at active regions.
Okay.
So that's a very unique feature.
Yeah. Yeah.
Yeah, and there's other things like when you observe it from one solar cycle to other solar cycle,
Okay.
uh, the sign of helicity sort of persists. So this trend persists.
Okay.
We know from like Joy's law and Hale's polarity law, like that one from one solar cycle to other solar cycle, the polarity switches and such.
Yes.
It's not the case with helicity,
Interesting.
specifically magnetic and current helicity. It
Okay.
stays the same from one solar cycle to other solar cycle.
Hmm.
It's in that sense, it's a new quantity that has been observed. I think the first observation sort of from 1990s or 1980s, late 1980s.
Yeah.
So it's a relatively new quantity and it has some very interesting characteristics that we want to understand better on
Cool.
how the helicity sort of comes from. So
Right.
that was the observational motivation for us.
Cool.
Going to theory, we can maybe jump to the second page over
Sure.
here.
Sure.
Um, so in theory, magnetic flux emerging from the deep solar interior has typically been modeled as idealized sort of a flux tube where you have
Mm.
a twisted flux tube structure which rises owing to buoyancy. So the
Hmm.
magnetic structure, when embedded in a stratified atmosphere, is buoyant and
Yes.
it's rising. And that's how we typically simulate and imagine the magnetic flux coming out in the solar atmosphere. And this is also observationally motivated because we see through AIA observations
Yeah.
of magnetic fields poking in and out in a cylindrical sort of a fashion.
Yes.
So that's how we have been always modeling the flux tubes, the so-called flux tubes in the solar interior. We raised a few questions to this
Okay.
in the sense that um, there are some simplifying assumptions which have been very aptly taken depending on when it was being studied, where the flux tubes were assumed to be isolated. So
Mm.
no magnetic field in the background. It was
Yeah.
completely isolated in a stratified atmosphere, sometimes without convection, sometimes with convection, and you just studied its evolution. One
Yes.
of uh, one of the earlier studies which focused on this kind of thing uh, came with a very interesting observation. If you put in just some cylindrical magnetic flux, which
Okay.
is not twisted, so there's no field line twist to the magnetic flux tube,
Yep.
it sort of disintegrates. It cannot rise through the background atmosphere
Okay.
because it doesn't have that sort of coherency which the tension force would ideally provide to it.
Yeah.
Uh,
Okay. I'm
so
with you. Hmm.
so as soon as you introduce twist to it, you see some coherent flux structures rising from the interior. So twist is an important uh,
Cool.
uh, physical characteristic of a flux tube. And with twist comes handedness. So twist could be positive or negative too. So we'll come to that. Um, but that was sort of the theoretical motivation where we wanted to study the flux tubes rising through the interior, but we didn't want them to be isolated. We wanted them to be embedded in some field structure and rise through it. So we understand what the implications of such dynamics could be,
Okay.
whether they are different or not. So that was the primary sort of motivation. And there's some other observation and theory based studies which have focused on studying the origin of helicity, like where the helicity comes from in the
Yeah.
magnetic structures.
Right.
And that's what is highlighted now, right? The sigma effect theory.
Uh-huh.
But maybe we come to it in the discussion section because that's where it would be most pertinent. Yeah.
Okay. Sounds good.
Yeah, so for the theoretical model, we have a very sort of a simple setup. We can go to the figure one because it shows
Sure.
the exact setup that we have.
Yeah.
So, so looking at like a cross section of the sun, what we are trying to simulate is the Cartesian box, which is there in the figure.
Mhm.
The Cartesian box doesn't go all the way up to the photosphere, but it covers a few density scale heights in the solar interior.
Okay.
The work is primarily focused on solar interior, so we focus on the near tachocline region. Where the flux tubes are presumed to be formed,
Okay.
and we study its rise through a few density scale heights in the interior.
Yes, I'm with
So
you.
the flux tube, twisted flux tube over here, that's the blue colored lines over here. You
Yeah.
can see the twistedness of the flux tubes. It's not isolated, so that's a feature that we are introducing. It's
Yes.
embedded in this red colored poloidal background field.
Mhm.
So
Mhm.
the flux tube has some twist. The background field has some orientation coming from north to south, and the flux tube is initially unstable because it's magnetic and the background it's in a stratified background. So just by the presence of magnetic buoyancy, it's unstable and it would eventually rise when we simulate it.
Yes.
Um, so that's sort of the initial setup. The background field over here has a unique characteristic where it's exponential in nature. So it's concentrated towards the base of the flux tube.
Okay.
Uh,
Okay.
and then as you go up in the atmosphere, it sort of decreases.
Okay.
And that's also motivated by some previous studies where, exactly.
Uh-huh.
So it's motivated by some previous studies where if you have turbulent convection in the convection zone, and if
Mhm.
you have any stray large scale magnetic fields, um, over the course of time, the field gets turbulently pumped towards the base of the convection zone.
Okay.
So it forms this natural exponential like
Structure.
magnetic layer.
Yes.
And that's sort of the motivation of putting in a exponential background field.
Cool.
Though we have checked the results, which I'm going to discuss, and it's uh, not sort of focused on the exponential nature of it. It could be linear, it could be constant, and the results persist. So it's robust in that sense.
Okay. Good.
Um,
Good.
One thing about the model is that we don't have convection at this moment. We are focused on just the flux tube dynamics in the presence of the background field. So convection adds multiple layers of complexity to the simulations.
Sure.
So at least for this work, we don't have any convection in the setup. So it's stably stratified, rising through a background field flux
Yes.
tube.
Initially.
Yeah.
Mhm. Mhm. Mhm.
And yeah,
Mhm.
the background state comes from the polytropic model, which is very standard. So theta is
Yep.
the temperature gradient that we impose. M is the polytropic index, and yeah, y dash is just the depth of the simulation box that we have.
Yes. Okay. I'm with you. Yep.
Yeah. So yeah, moving forward. Uh, yeah, I think we can go to the results section. I think that's what I have next.
Alpha type. Okay. I was just checking
Yeah,
the
so we
boundaries
have
of your box there.
some of
Yeah. Yeah.
the these are like standard boundary conditions of fixed temperature at the top, stress-free boundaries, and we have outflow boundary conditions, which are also some sort of unique, where you don't have flux coming in inside the box, just because um, it complicates things. And even if you don't have outflow, the results again are robust to the boundary
Yeah,
condition. So it's just a matter of convenience here. Yeah.
fine, good. Just checking it. Okay.
Yeah. Um, and to the initial flux tube, we impose some sort of density gradient feature.
Yeah, okay.
So the flux tube is naturally buoyant, so it has a density deficit because it's in a background sort of a stratification.
Uh-huh. That's
We
fine.
impose an additional sort of a along the tube perturbation to make the center portion of the flux tube more buoyant compared to its legs. Uh,
Okay,
this what has been observed and what has been simulated in the past. So we follow that tradition where the central portion arches and the flux tube forms this arching rising structure with omega-like loops and such. So that's what we choose. And it gives
cool.
this simulation the marked 3D nature that is also one of the features of this work.
Cool, very nice. Okay,
Yeah, we can go ahead to the figures now. So I'll discuss what the
okay.
simulation results sort of look like.
Gonna zoom out a little bit here to get the global, and then we'll zoom in as need be.
Yeah, sure. This is the sort of canonical simulation that we have. So you have a flux tube. What the figure is showing is basically normalized B squared. So it's the
Mhm.
magnetic field sort of amplitude, and it's normalized through all the time. So the figure shows the time evolution as the flux tube starts emerging. Now, in this case, what's unique is that there's no background field. So it's a canonical case,
Yeah,
sort of simulating what everyone has already done.
good.
Uh, so it's a flux tube which is twisted. We don't see the twist in here, but it's anti-clockwise in nature. And
Yes.
as we initiate the simulation and see the evolution, it see that the central portion starts arching. You
Yep.
have these complicated vortices getting formed. There's all sort of complex things going on where you have some drainage along the flux tube,
Yeah.
some drainage of magnetic flux going into the vortices. So these vortices sort of drive the eventual rise of the flux tube. The
Okay.
initial rise is predominantly by magnetic buoyancy.
Uh-huh.
The vortices start, they basically advect the flux tube out into the atmosphere.
Oh,
Um,
yes.
yeah, eventually it rises to the top of the simulation, which we treat as sort of the end point of our simulation case,
Right.
where it has this marked 3D nature with arching flux tube and whole lots of vortices and everything going on. So that's sort of a very typical flux tube rise that we have always seen in many simulations before in many different studies.
I think you said it earlier, but just remind me, how many pressure scale heights or density scale heights are in the box?
Yeah, so it's about three density scale heights,
Three density. Okay.
and yeah, I
Okay.
should I should I should check that, but I remember it being two or three density scale heights
Mhm.
in that range. And again, like if you change the density scale heights, unless you are going up to the top of the box,
Yeah.
it doesn't necessarily change the dynamics as such. It just balloons up the rising flux tube as it's
Yeah, idle scale. All right. I,
yeah.
I just curious what it was in the actual box. We're good. We're good.
Yeah.
Cool.
So,
Okay.
so
There's
this is
no
the
background field.
yeah, there's no background field. This is the canonical case. Everyone has done it before, and it's a nice place to start from. So now we introduce the background fields and see how these dynamics would change and
Yes.
eventually what the implications are.
Cool. Okay.
Yeah, so going forward, figure 3 sort of shows the first case over here where you have a flux tube, the same flux tube as before, so it's anti-clockwise twisted,
Yes.
and introduce a background field. Now these are volume renderings, so we have cut out all the magnetic field of the background field that lies on top of the flux tube.
Okay.
Um,
Okay.
it's just a visual thing where it makes it easier to sort
See
of
what's going on.
observe what's going on the dynamics.
Yep.
Um,
I'm with
so
you.
uh, yeah, the figure shows again the same thing. It's normalized magnetic field intensity, B
Mhm.
squared.
E squared
Um,
normalized.
the
Mhm.
flux tube is twisted anti-clockwise. The background field is oriented in the positive x direction. So, so if you sort of zoom in on the first figure over here, the
Yeah,
first
sure.
section, you'd see that there's orientations there. So the x-axis, it's aligned along the positive x-axis,
Hmm.
and we
Hmm.
take it from there. And now we start seeing
Twist.
how it evolves.
Yep.
Some of the interesting features that we'll see in the first few time steps only is that um, the flux tube is again getting arched because that's an initial condition that we have provided.
Yes.
However, the formation of vortices seems to get hindered a bit because it has this connectivity with the background field.
Yeah.
There's some flux drainage going on. It hampers the efficient formation of the vortices.
Vortices. Yeah.
So it makes the rise sort of a little difficult here. It's rising, but it's rising slowly if we compare the timescales from the previous case, canonical case.
Yeah. So let's see. So by the time we got to the end here, we're at 59. By 43, we're definitely uh
Yeah, midway through the box or
flipping up.
something.
And but in
Uh,
this one, yeah, it's slower to react.
yeah, it's slower to
Yes.
react and it reaches sort of slowly. But there's a twist strength and there's a background field strength. So as you change the background field strength,
Yes.
it affects the dynamics too. In this case, we have imposed the background field, which is such that it's about 5%. So it's a very weak background field.
Okay.
It's 5% of the flux tube strength at the center of the flux
Ah,
tube. So
yeah,
we
yeah,
are taking that as a measure point. It's a very weak background field compared to the flux tube strength, just about 5% of the flux tube.
yeah. Okay. Okay.
But interestingly, you'll see that, okay, initially it faces some resistance because it's in an underlying field.
Mhm.
But as it starts rising, it again forms the vortices, and it looks very much similar to the canonical case that we saw. So it would
Yes.
seem like that the introduction of magnetic field, the background magnetic field, hasn't changed the dynamics as such.
See.
Um, but if you increase the background field strengths,
Yes.
then it's a different scenario altogether. Um, but what's interesting here is that what happens if we flip the orientation? So there's the strength of the background field and there's the orientation of the background field.
Fair enough. Okay.
The flux tube has some twisted orientation. The
Mhm.
background field has some orientation. In this case, we aligned it in the positive x direction.
Okay.
Happens if we just flip the background field orientation? That was the question that we asked.
Okay. Okay.
If we go to the next figure, figure 4, that's what it shows. It's the
Cool.
same thing and it's showing b squared. So you don't see the orientation in the
Yeah. Oh,
color,
yeah. Yeah.
but it's aligned in the opposite direction. So it's going in the negative x direction,
Yeah.
and the flux tube is the same twist
Woo.
anti-clockwise. And it's
Stuck.
the same strength of the background field, 5%
5%.
to the flux tube. Yeah.
Okay.
And immediately you start seeing very different dynamics here,
Indeed.
even at
Ah,
this weak field strength.
that's
The
great.
flux tube, the flux tube sort of completely disintegrates.
Yeah.
It doesn't really rise through the background field. So it shows this
Interesting.
very contrasting sort of dynamics just by virtue of playing with the background field orientations at very
Yes.
weak background field strengths. So like basically the moral of the story is that first of all, flux tubes isolated might not be that great an assumption.
Fair enough.
Introducing background fields through which it has to rise may give us more idea about the dynamics, real dynamics of the flux tubes.
Okay.
Uh, Secondly, even really weak background field can impact the dynamics quite a bit.
Yeah.
Uh, And sort of the orientation of the background field matters too.
Yes.
Now, this is again part of the bigger results. It's the relative orientation of the background field compared to the flux tube twist.
Yes.
So it's the relative orientation that we care about, and that would dictate the dynamics, as we'll see later in the results about why this is happening.
Okay.
We'd see that it's the relative orientation and not just the orientation of the background field.
Fair enough.
Yeah. So yeah, again, very surprising set of results where you don't see flux tube rising in one case, you
Yeah.
see flux tube rising in another case. So
Yep.
it's showing something about this asymmetry in rise that you observe based on the orientations of twist and background field that you have. So this should ring a bell about helicity, and we'll come to that in a few minutes. Yeah.
Yes.
Um,
Can see where this is going. Yes.
yeah.
Okay. Good.
And we run a broad range of cases with various flux tube twist strengths, various background field strengths. So in this figure, we show a very compact sort of set of results. And the first few ones were more of visualizing how the rise is actually occurring. In this case, we plot the rise of the flux tube. So we are plotting the sort of location, the vertical location of the flux tube as
Mhm.
it's evolving in time. So the YFT is sort of a quantitative measure of where the flux tube is in vertical height as it's evolving.
Yes.
And the sort of B subscript S, that's the background field strength compared to
Mhm.
initial flux tube. Initial flux tube is the same, the twist is the same, the strength is the same, everything is the same.
Okay.
It's just the background field that we are varying. In
Okay.
a particular subset, in a particular figure, we are varying the strength. And as we go to the figure B, we are varying the orientation of it. So we see both the characteristics of how the strength
Got it.
and how the orientation matters.
Yep.
So if you look at figure 5A over here, as we start increasing the background field strength, the
Hmm.
rise becomes much more complicated and much more hard to decipher. The rise sort of hampers around 15% of the background field strength. So
Yes.
if you look at like figure A over here, at the first
Mhm.
one, you'd see like the sort of pink dots, they are like around 15% of the background field strength.
Yes.
The rise is very slow, and we sort of cut it off once the dynamics are so complicated that measuring the location of the flux tube gets sort of impossible.
Ambiguous.
Yeah. So,
Yes. Okay.
so it's just showing like how difficult the dynamics could be once you have the background field. The red colored case is the background field zero case.
Right.
So that's the canonical case that we already saw
Right.
in the second figure.
Two.
And
Yep.
as you start increasing the background field, you'd see
Mhm.
like the slope is also increasing of all the curves. So the rise is becoming slower. So the flux tube is rising slowly, and eventually it sort of almost kills the rise. The flux tube, you don't see a coherent structure rising.
Yeah. Also, you get a big change around 10-15%.
Yeah, so these sort of 15 and 20% cases, they are very hard to track in terms of tracking the flux tube. That's why you see those sort of weird jumps and everything going around. But it just shows that there's no coherent rise of a flux structure.
Right. And
Now, if you go to
the 0.05 case here in blue, this is what we saw in figure 3.
yeah, that's what we
Right.
saw in figure 3. So that's one of the cases that we saw through volume renderings. Um, if you go to figure 5B,
Hmm?
the background field strengths are the same. It's just the orientation of the background field that has changed. Everything else remains the same, just the background field orientation changes.
Wow.
The 1% case, the very weak case, you'd see that it gets slower and it sort of rises to the top. But again, it's hard to sort of track and follow the flux tube. But at a very weak strength, like 3% or 5%, we really don't see any rise. It just sort of breaks apart and completely
Right.
get disintegrated. So in that sense, it's a very unique sort of a character of rise that we see, and it's a markedly different nature of rise depending on how your background field strengths and orientation are compared to the
Yes.
tube strengths and orientation. So we could do the exact same thing, just vary the orientation of the flux tube. So it's anti-clockwise. We could make it clockwise and keep all the background fields oriented in the same direction. It would
Yeah,
be the same. So it's sort of
exactly.
a mirror symmetry sort of a thing going on where
Yes.
you have to focus on one of the orientations. We focus on the background field orientations for this study.
Fine.
Anyone wanting to replicate this, they could just change the twist and keep the background fields the same. It would give the same results.
Same results. Yep.
Yeah.
It's the relative. Yep.
So,
Cool.
so again, like now we go to what are the reasons behind this? Why is this sort of thing happening?
Yes.
And that's where things get interesting when you start looking at how the forces are behaving when you have a background field and when you don't have a background field. So we go to this next figure, which shows a very simplified picture of how the tension force is going.
Yeah, well, tension. Okay. Vertical tension, figure 6.
Yeah. So this figure is sort of a 1D line cut through the center of the flux tube.
Okay.
So it's going in vertical direction. So you are going up in the box through the center of the flux tube.
Yes.
And this is just at the initial conditions. So this is at t equals to 0. You have we have sort of zoomed it. So the Y domain is from 0.3 to 0.7, even though the box size is very different and very large. We're just trying to focus on the initial structure of the flux tube and the tension forces there.
Okay. Okay.
So you have the zero background field case here, which is the red curve over here marked in circles. And it's symmetric, and it has to be symmetric. It's sort of obvious because there's no background field. You just have a uniform twist of the tube. The tension force acting at the top of the tube is inward. The tension force acting at the bottom of the tube is upward, and they sort of cancel out. So the volume integral of the tension force is 0. The net oppositely directed tension force provides it the cohesion that it needs to rise through the background stratification. So symmetric, but the net tension force is 0 on the flux tube. Now, once you sort of introduce the background field, right? You put in a positive background field orientation. So a 5% case over here. And it sort of moves things in a very different way. So you have this increase in sort of localized tension at the bottom. So if you imagine this cylinder of a flux tube and the tension force acting at the bottom, which is upwards, it's slightly larger compared to the canonical case when you have a positive background field. And if you focus right away on the negative background field case, there's a lower sort of a upward push to the flux tube. And if we go to the top of the flux tube, which is like around 0.6 or so, there are similar changes. There's a net sort of a downward tension force, which is slightly lower in the positive case. But in the negative case, there's a slightly more downward force, tension force acting. So looking at it like in a 1D cut makes things much easier in terms of visualizing the dynamics of why it's happening. So it's giving you this idea that, okay, tension force is really changing when you have this background field. And when you think of it, it sort of seems obvious that yes, you have some background field which is oriented in one direction. There's some localized twist. Once you have background field orientation and the twist at the bottom sort of getting enhanced, so the local magnetic field there gets enhanced. So your tension force, which is like B squared over the curvature,
Yes.
gets enhanced. So you have a sort of a stronger upward push. If you have those aligned in the opposite direction, the net magnetic field at the local bottom of the flux tube
Uh-huh.
uh, gets sort of decreased, and the B squared over there, like the B dot grad B, which you look for in the tension forces, that sort of gets reduced. So that upward push, which the flux tube would ideally get because it's buoyant and it has this tension force,
Cool.
gets sort of skewed in a dramatically different ways for one case and the other case. So
Right.
that sort of is the main sort of a picture of what's actually
Cool.
going on. There are other magnetic forces like the buoyancy force. Once
Sure.
you increase the background field, the buoyancy force also gets skewed in one or the other way. But the
Right.
buoyancy force is always acting upwards. So the magnitudes are sort of decreased by very small amounts, where uh, the
Right.
rise is sort of like slightly so like looking at buoyancy forces, you see the same skewedness where the
Okay.
introduction of the background field pushes one case slightly more buoyant, the other case slightly less buoyant.
Yeah.
But looking at tension forces, it shows you like how the positives and negatives are working and how things are getting sort of canceled out. In one case is like not really rising. So one
Cool.
case has a net downward force going on, one case has a
Yes.
net
Yes.
more upward force going on. So there's some dynamics that get introduced because you have a field environment. So you have a background field environment rather than a field free environment.
Okay. Cool. Cool. Very
Uh,
nice.
yeah, so going forward, we'll look at these tension forces because it's like the 3D calculation.
Uh-huh.
Uh, Looking at 1D in the initial conditions is useful, and it's very sort of
Definitely.
helps us understand things. But we look at the tension forces in deep detail, where we try to understand what actually is going on with the tension forces and all its component, and also its time evolution. So is it like just a initial condition thing, or is it evolving in nature, and how the
Okay.
tension forces are changing? So
Okay.
yes,
Nice.
uh, we go ahead and look at the next figure.
Sure. 6. Took a look at the little tension. Yeah. Total tension.
Yeah, so this is like a volume integral of the tension force that we are doing. So
Mm-hmm.
we are trying to track the flux tube. We are calculating all the vertical tension force components, and we are sort of integrating it over the flux tube
Okay.
and evolving with time. So you have
Sure.
that's the initial condition. So t equals to 0, which we saw in the previous figure.
Yes.
And it showed you like, okay, one is like net positive, one is like net negative. The positive and negative cases, as you can see here, at t equals to 0. So if you look at
Yes.
t equals to 0, the time 0, you see
Uh-huh.
that for the canonical case, the net tension is 0, which is what we discussed.
Mhm.
Once you start introducing background fields, one or the other orientation, the net tension force is either positive or negative depending on the orientation. So you see it at t equals to
Okay.
0, which we saw. But as we start like time evolution,
Makes sense.
and it's a 3D thing, so how does it evolve? So we see a very
Yes.
interesting case where it's clear that introducing one orientation of background field, the positive one and the positive 3%,
Mhm.
green colored
Green. Yes.
ones, um, they give you a net positive upward force.
Little
When
bit. Yes.
you have that sort of a orientation.
Uh-huh.
When you have the negative background field cases, so the blue colored figures,
Sub.
colored lines, you have a net negative tension force acting on it. So there's a net tension force, but it's negative. So
Rises.
it again paints the picture of why the dynamics were so different.
Okay.
The
Nice.
0% case is sort of unique here because it starts with a net tension 0. As it starts evolving and forming these vortices and it's sort of increasing in size, the flux structure as it's rising, there's a sort of a net upward push to the flux tube.
Yes.
But it rises to a certain point, it's an increase in the tension forces, but eventually it sort of starts decaying. There's magnetic diffusion and such things. So
Right.
a whole lot of other things lead to some small decay in the vertical tension force. And these are sort of initial times also. So we focus up to time 10. We can go ahead and like look at like figures up to time 50 or 60. It's sort of the similar behavior, transient tension force where it's decreasing because of diffusion, but it's more or less,
Yeah, yeah.
it's more
Okay.
or less has this characteristic of a positive and a negative
Capital rises.
differential in the other cases. So
Very cool.
um, and just because we have the 3D cases, we dig deeper. We look at individual components of the tension forces too,
Okay.
because you could decompose the vertical tension force into some tension force components which are across the tube and
Yes.
some which are along the tube. So
Yes.
maybe that gives us some more idea about the dynamics. So we do that in the next figure.
Cool. Okay, so that's total. Let's look at some. Oh, here we go. There's all the discussion on the parts, the people, partials. Let's see. I think what I'm going to do on this one is I'm going to zoom out so we get the global, and I'll zoom in as need be.
um, yeah, so maybe we focus on the figure 8B, the central figure.
Okay,
B, that would be
plus
instructive,
three.
and we can look at sort of the legends too, like which components are which.
Yes.
Um,
Take a look at 3% positive.
yeah, 3% is also great.
Okay.
So in this case, we have different components of the tension forces, right? So B dot grad By. So we
Mm-hmm.
at just the vertical forces. So you have different components like Bx, d by dx of By, by, sorry, By, d by dy of By,
Yes.
Bz, d by dz of B.
Mm-hmm.
So these are sort of the three components, right? The sort of yellow colored curve, maybe it's like mustard colored curve or something. It tells you about the along the flux tube component.
Yes.
So,
Exactly.
sorry, across the flux tube component. So these are sort of the horizontal components across the flux tube. And then you have the blue curve, which is like along the flux tube. So the flux tube is aligned in the Z direction. So that's the along the flux tube component here.
Cool.
Now we
Okay.
are also looking at some initial time steps like up to time equals to 10. What we'd see is like the sort of across the tube components are very dominant in the total
Yeah.
tension force.
Yeah.
So as the flux tube is evolving, it's sort of expanding in size. It
Yes.
has the vortices forming. So there's whole lots of complicated horizontal components of sort of along the tube components of tension, vertical tension force, which are coming and giving it sort of a vertical push.
Cool.
So we notice that the horizontal components, the along the tube components, are sort of predominantly dictating the rise over here.
Yes.
Um, as we sort of evolve the flux tube and it gets
Mhm.
more complicated, you have along the tube components coming into, so like something like a bz d by dz of by,
Yes. Blue
it
here.
sort of starts increasing and it's start giving,
Slowly.
because it has this 3D market structure, it could have some positive or negative components along the tails of the flux tube,
Quickly.
and that could also contribute. um, but what we see predominantly is that the along the tube components, which are sort of, I visualize them in the sense that they're related to the flux tube expanding and rising,
Yeah.
sort of dictating the important components of the vertical tension force. So, and going at like maybe the negative 3% case,
Yeah. Let's look at the -3. Oh yeah. Uh-huh. Uh-huh.
so it's very clear that along the tube components have been very disproportionately negative. So they give you a very strong downward force
Mhm.
uh, right in the initial conditions and also as it's evolving. So
Mhm. Mhm.
it's a sort of a persistent feature and effect that the flux tube has to face as it's rising through this background field. So
Okay.
so we conclude in this work is that the tension forces get show very markedly different characteristics
Yes.
when you have an isolated flux tube case and when you have a background field embedded flux tube. And depending on the orientations,
Yes.
that feature also has another second degree of complexity where it could aid the rise or it could hinder the rise. So it could make things sort of very challenging for the flux tube to rise, and it could maybe even help the flux tube to rise.
Okay.
So at this point, I mean, we should go back sort of to helicity in terms of understanding what helicity was and how we can link this sort of dynamics to helicity. So
Okay.
yeah, we
Cool.
talked about helicity as like focusing on current helicity. It was magnetic field dotted with the current density. So current density is curl of B. Uh,
Yes. And that was way up here at the top where we covered that. There we go. Hmm.
so it's current density. Just a second. Yeah, so it's current density dotted with magnetic field.
Yeah.
Uh,
JW. Hmm.
so in our case, when you transform this sort of a 3D Cartesian model to a solar case, you have the twist of the flux tube. So that gives you some sense of del cross B. So the curl of the magnetic fields. Uh,
Yeah. It's a sign.
in our case, we have a anti-clockwise sort of a flux tube. So if you do a curl, it's sort of coming out of the screen here.
Yeah. Fine.
And the background field, which sort of dictates like the B dotted with the curl of B. So you have this background field,
Yes.
and um,
Yes.
the ideas are that the flux tube has been formed by the stretching of this background field where the omega effect acts on the background field initially to
Uh-huh.
form this flux tube, which
Uh-huh.
in our studies we have assumed that the flux tube exists.
Yeah, it already exists.
Yeah,
Yes.
it already exists. It has been formed. But the idea is that it has to be formed by the stretching of this background field by the omega effect, which is an important sort of a solar dynamo concept where
Hmm.
the stretching of the magnetic fields leads to this concentrated flux structures that are formed. So
Yes.
the orientation of the background field going sort of in. So if we maybe go to the figure one,
Yeah.
it can paint the picture
Yeah. Yeah. This
nice.
is better.
So
Hmm.
you have the red colored lines. Those have been stretched in sort of a longitudinal way over here in the toroidal fashion
Hmm.
by the differential rotation to form this flux tube.
Yeah.
Now this flux tube has this curl, which is sort of pointing in one direction, and you have this magnetic field going in. So it has a helicity. So the flux tube has some helicity to it. In this case, in this particular figure, it has B dot curl B is negative. So it's a negative helicity flux tube.
Okay.
We could
Okay.
similarly look at a flux tube which is in the southern hemisphere.
Yes.
If
Yes.
the twist same, but the background field orientation is in a certain fashion, but the axial field sort of changes the direction over there. So B
Yes.
dot curl B could be like positive or negative depending on how you are arranging it.
Okay.
Uh, but what it would do is, in this case, this is the scenario where we saw a sort of a background field aiding the rise of the flux tube.
Correct.
So you are looking at a northern hemisphere case
Uh-huh.
where the flux
Good.
tube has negative helicity.
Good.
And the background field is aiding the rise of the flux tube,
Yeah.
sort of pushing the flux tube up. Oh, okay. Somehow Siri took notice of something I said. Sorry.
It's all good.
But if you go to the southern hemisphere and if you have all the same orientation, it is again going to be negative helicity.
Yeah.
But the background field orientation and the flux tube orientation are such that it doesn't, by our simulation, it doesn't help the rise. So
Right.
it could be negative
Very
helicity in the
cool.
northern hemisphere,
Very
but
cool.
not rise.
I got it. Very cool.
So it leads to this observational correlation with helicity that we observe,
Mhm. Mm.
even though again it comes with all the cautionary tales that we are not simulating the rise up to the
Top.
surface.
Yeah.
We don't have convection in our system.
Right.
um, so
Excellent.
but with all those things, we have some 2D cases which we have published in this series of papers. So this is like, I think, 3 or 4 series of papers where we
Yeah.
have looked at different physics and
Cool.
investigate cases with convection too in 2D. But
Human.
there's
Yeah.
there's some sort of a explanation for how the helicity gets originated. It could be from the initial flux tube twist. There's a alternate theory which has long been proposed, and it's like one of the leading theories, which is the sigma effect. And
Oh,
the sigma effect says that if you have a thin, untwisted flux tube,
okay.
which rises through the convection zone in the
Uh-huh.
presence of rotation. So the
Okay.
action of this rotation and convection on this rising flux tube is such that it sort of arches the flux tube and it provides this one component of helicity called Reith. So
Okay.
twist is the axial sort of the flux tube twist is along the axis of the flux tube. So
Okay.
it's twisting of the field lines along the axis. Once the axis also gets twisted, when the flux tube is rising, that component is the right. So,
Okay.
so there's multiple components to helicity, and it's the right component which gets one particular sign because of
Yeah,
the
sure.
turbulent nature of convection, and there's a rotation which gives it a sign. So it has one component, and because magnetic helicity and current helicity are believed to be conserved, magnetic helicity is believed to be conserved in ideal MHD,
Yes.
and even in non-ideal MHD, it's conserved to a very large extent. So
Yes.
it's a very important quantity in that sense. You have this right coming in because it's rising through this turbulent rotating convection.
Uh-huh.
Because the magnetic helicity is conserved, it would get an equal and opposite sign of twist.
Yeah. Yep.
So that's what you measure at the surface from observations, because observations are also limited and they can only measure one component of helicity. The component that gets measured, the sigma effect says that just because of the turbulent nature of convection and the rotation, the flux tube, which is rising from the interior, gets some sign of twist, and they show that that sign is commensurate with the observations of helicity.
Cool.
Um, so it's a very neat and very interesting
Great. Great.
theory.
Yeah.
And they have shown it. This work is by Dana Longcope and I'm forgetting the first name of the other author, but the last name is Clapper and Alexei Pevtsov. So it's a nice, very interesting theory. It comes with some limitations that they assume thin flux tubes. Again,
Mhm.
if you have thin flux tube versus some sort of cross section, the dynamics can again be very different.
Yeah.
And they start with initially untwisted flux tube, which is sort of again very difficult to comprehend because they won't rise. The thin flux tube models have some prescriptions to make them rise, but untwisted flux tubes are known to not rise under this um,
Right.
stratification. So it's an interesting question to ask about which sort of dynamics, and it's a purely hydrodynamic thing. So they are not talking about like they have a magnetic field, but it's the sort of hydrodynamic nature of the convection and the turbulent rotation that's sort of impacting the helicity sign over there, and is leading to the observations of solar hemispheric helicity rules. In our case, it's predominantly the nature of the flux tubes and that they have to rise through a background field. So it's sort of a magnetic effect which we are showing. So we propose this second alternative where we say that it could
Cool.
just be that the flux tubes are rising through background field and they get this filter effect where some rise more faster, some rise less faster, or don't rise at all.
Yes.
And that could explain this helicity observations.
Yeah. Yeah.
Yeah,
Okay.
I
Very
mean,
cool.
yeah, it could very well be that both these phenomena interact and have some sort of impressions on the final observations that we see. So over here, the citation to Noon Wade
Yeah.
2023 at the very top. Um, so that's a, thesis by my friend and colleague who's working with Nick Brummel, and they are investigating the impact of rotation, convection, and the background field. So sort of everything included, and trying to quantify how the sigma effect is contributing to helicity evolution, uh, and how the magnetic sort of filtering effect that we have discussed here is impacting the helicity signatures observed in the sun. So there's two different theories now. Initially, we had only one, but it would be
It was
good
good.
to understand and investigate which ones sort of contribute more. Um, so
Mhm.
in this regard, there's some initial work with observations. So the second citation here by Liu et al. 2024, um, this got published in the same volume of ABJ in which this paper is published. And
Yes, it
they
was.
they're Yang Liu. He's the leading author. He looks at observations and looks at observations of kinetic helicity and magnetic helicity. So magnetic twist, magnetic right, everything, and tries to find correlation between them. Now observations are focused in the solar atmosphere. Kinetic helicity observations are from helioseismic measurements going up to like 10 to 15 megameters deep.
Yeah.
Um, they are trying to find correlations between them. It's important because in the sigma effect, the kinetic helicity, which is dominated by turbulent rotating convection,
Uh-huh.
has a marked impression on your helicity that you're going to observe. So there
Sure.
has to be some sort of a correlation or anti-correlation. And Young's paper discusses that, and they sort of find that there's no correlation between kinetic helicity
Okay.
and magnetic helicity, even though it's just in the first 10, 15 megameters. So again, it comes with lots of cautions, but it gives us some initial indication that maybe kinetic helicity isn't dominantly impacting the helicity in the near surface. It might still be very important deeper down,
Deeper down. Yeah. Okay.
or yeah, we need more observations, better observations, more sort of comprehensive, even more comprehensive studies going across solar cycles to understand how these things are going. And of course, we are looking at more simulations. And Jacob here, he's looking at simulations too. And we are trying to club these simulations with observations from Young and trying to understand this better.
Very cool.
Thanks.
Very cool. Bhishek, I want to thank you so much for walking us through your very lovely article.
Thank you so much. Thanks for
Very
having me.
nice. Yeah, and you did cover a little bit there at the end on sort of, what do we do next? So let me, and I think you covered that pretty well. So let me just bear down a little bit part of it. So what are your next plans? Let's say over the next couple of years, where's your focus going on this?
We're trying to collaborate more with people doing observations like Young and Rudy Combe, who look at kinetic helicity and magnetic helicity observations.
Mm-hmm.
we are reaching out to them in like, oh, what do you observe? Is there something that can inform our simulations, and we can sort of try to either reproduce or try to better understand what the observations are? And we try to tell them like, okay, this is what we are seeing from observations. That twist is sort of the important helicity observer that we are seeing. These are the features that are coming out from our simulations, and we have a whole suite of simulations, so we can calculate some characteristics and such. So we are discussing those sort of ideas where we collaborate between observations and simulations
Nice.
uh, to
Good.
understand. But there's also complete theory and simulation work going on where we are doing it in a convecting box. There's background fields, and there's convection, and there's flux tubes. So it has the sigma effect
Yeah.
going to, and it has the magnetic filtering sort of effect going to. And
Nice.
that gets more complicated, and measuring and analyzing things
Yeah.
is much more difficult there to
Hmm.
figure out, okay, which one is acting when, which effect, and trying to quantify them is sort of the main pursuit next.
Yeah, right. Very cool. Very nice. Well, it'll be really exciting to see this develop, fuzzy me, over the next couple of years as the simulations improve, and then that you know, coordination, that back and forth with observation is always wonderful. So it's been really cool to see this develop over the next couple of years.
Yeah,
Right.
you're working on it.
Yeah. Yeah. And that will do, everyone. And I hope this made your astronomy day, solar day, just a little bit better. And we will see you on the next one. Bye-bye.
Thanks so much.
Thank you.